Hi everyone, welcome to Math 70. This lecture video is section 4.3 and it covers the rules of exponents and exponential notation. So I just want to go back to the previous video really quickly and take a look at that last example, which was 2x squared times x cubed minus 4x plus 1. And I use the box method where I had the 2x squared here and the x cubed minus 4x plus 1 on top. And this box right here became 2x to the fifth. And what we're doing today is we're exploring and understanding why you get 2x to the fifth when you multiply x cubed times 2x squared. Just to finish this example, minus 8x cubed plus 2x squared, which gives me 2x to the fifth minus 8x cubed plus 2x squared. But we're focusing on why we get this answer when we multiply x cubed times x squared times 2. All right, so first of all, exponential notation is simply a compact way to write repeated multiplication. If I want to write 4 times 4 times 4 and I'm feeling lazy, I say, well, I'm multiplying 4 by itself 3 times, and that's my exponential notation. 4 to the power 3 is how we normally read it. We might say 4 cubed or 4 to the third. But this notation always means take the big number at the bottom and multiply it by itself as many times as a small number on the top. When I write 4 to the third in exponential notation, this big number is called the base, and the small number is called the exponent, or sometimes the power. So that is our exponential notation. It's simply a way to do repeated multiplication. We can do repeated multiplication of all sorts of things. For example, I could take 1/3 and multiply it by itself 5 times. And again, that's a lot to write. So instead, I'm just going to do that's 1/3 to the fifth power. All right, that's our exponential notation. It works for powers of x as well. X cubed is just x times x times x. 2x squared is 2 times x times x. And guess what happens when you multiply them together? If I take 2x squared times x cubed, that's 2 times x times 3 more x's, which is 2 times x to the fifth, which is exactly how we got this answer right here. X cubed times 2x squared is 2 times x multiplied by itself 5 times. And this introduces our first rule of exponents. And that rule says, if I have a number raised to a power, and I multiply that by the same number raised to a different power, the fact that exponentials is repeated multiplication means that I could write it out. Oops, I think I wrote it out wrong. Let me try again. 4 to the third is 4 times itself 3 times, and 4 to the fifth is 4 times itself 5 times. All of these are multiplication, and I have 8 in total. And 8 is exactly what you get when you add the two powers. Multiplying the same base with different powers or different exponents multiplying the same base with different powers is the same as adding the powers. So as an example, if I have 2 to the 7th times 2 cubed, that's 2 multiplied by itself 7 times, and then multiplied by itself 3 more times, which is 2 multiplied by itself 10 times, which is what 7 plus 3 equals. Every single one of our exponential rules comes from the fact that exponents are repeated multiplication. And I want you to keep that in mind. Here's another one. If I take 5 to the 7th and I divide it by 5 squared, well, because exponential notation is just repeated multiplication, I could write out that repeated multiplication. And the division tells me I get to do some cancellations. I'm going to make that 5 cubed. I like that better. 5 to the 7th divided by 5 cubed. With all of these cancellations, it leaves me 4 5s multiplied together, which is 5 to the 4th. And 5 to the 4th is exactly what you get if you take the top exponent and subtract the second exponent. So to divide the same base with powers on top and powers on bottom, you just subtract the powers, top minus bottom. Let's do another example. 7 to the 4th divided by 7 squared is going to be 7 to the 4 minus 2, which is just plain old 7 squared. It doesn't really matter how big your numbers are. I could have 13 to the 19th power by 13 to the 12th power. And that's going to be 13 to the 19 minus 12, which is 13 to the 7th power. And you can check this if you wanted to sit down and write out 13 multiplied by itself 19 times, and then divide that by 13 multiplied by itself 12 times. After cancellation, you'd have 7 13s left. It works just as well for variables. X to the 7th over x squared. Well, that's 7 x's on top, 2 x's on bottom. After cancellation, I'm left with x to the 5th, and 5 is 7 minus 2. Again, it comes exactly because of what exponential means. It means repeated multiplication. Now, this rule actually leads us to another really helpful rule for our exponential notation. Did I write rule 2? Here's rule 2. Our next rule comes from the following example. What if I have 2 to the third and divided it by 2 to the fourth? Well, using what I know about exponentials, I can write that as 2 times itself 3 times, divided by 2 times itself 4 times. And after canceling, I'm left with 2 times 2 times 2 all gets canceled into a 1, and 2 times 2 times 2 times 2 gets canceled into a 1/2. 2 to the fourth over 2 to the third is 1 over 2. But I could also use that other rule I just developed, which says, aha, that should be 2 to the 3 minus 4, which is 2 to the minus 1. And this is our rule. Any number raised to the -1 power can be written as 1 divided by that number. So a couple examples. 7 to the -1, I can write as 1 over 7. I can even do this with negatives. -3 to the -1 is 1 over -3. And x to the -1 is 1 over x. This becomes very important. Any number raised to the -1 power can be written as 1 divided by that number. Our rules just kind of build on each other because the next rule comes directly out of this. Four. Any number raised to a negative power, not just -1, but any negative power, can be written as 1 divided by the number raised to a positive power. Let me show you what I mean. We know that 3 to the -1 is equal to 1/3 from our previous rule. And at the beginning of this video, I showed you that 1/3 times 1/3 times 1/3 times 1/3 times 1/3 is equal to 1 over 3, all raised to the 5th power. But if I looked at this 1 over 3, I could write that as 1 over 3 to the 5th. I'm sorry. If I can write 1 over 3, I could also write 1 over 3 to the 5th, which is 1 over 3 times 3 times 3 times 3 times 3. And we can split that out as 1 over 3 times itself 5 times. And each of these is a 1/3 to the -1. So this becomes 3 to the -5. Any number raised to a negative power can be written as 1 divided by that number raised to the positive power. 7 to the -2 can be written as 1 over 7 squared. Y to the -8 can be written as 1 over y to the 8th. And there's another extension to this rule that follows, but I'm not going to demonstrate in great detail. I'm just going to say this also works the other way. If a negative power is in the bottom of a fraction, which we call the denominator, you can move it to the top of the fraction, which we call the numerator, and make the power positive. Let me show you some examples. 1 over 8 to the minus 3, I can just write as 8 cubed. I take that 8 to the minus 3 and I move it to the top and I change the sign. 1 over y to the minus 5, I can write as y to the 5. So putting these two rules together, you can switch top and bottom of the base if you switch plus and minus of the power. That's not the most mathematically precise way to state this rule, but I find it maybe easier to remember. So let's do something a little more complicated. Let's look at x cubed over y to the 5th. I can make that x cubed go in the denominator by making it a minus 3. And I can make that y to the 5th go in the numerator by making it a minus 5. Another example, maybe I have z to the minus 2 over w to the minus 4. I can make that z go into the denominator if I make the negative power a positive power. And I make the w go into the numerator if I make the negative power a positive power. One more example. 5 to the minus 3 over 7 to the positive 2. All sorts of ways I could rearrange this. I'm going to list a few of them. I could make everything have a positive power. So that'd be 5 cubed times 7 squared. Or I could make everything be in the numerator. So that could be 5 to the minus 3 times 7 to the minus 2. Or I could just switch them and I could have 7 to the minus 2 over 5 cubed. A lot of different ways to rewrite these, and they all depend on the same rule. You can switch the top and bottom where the base is if you switch the plus and minus of the power. And we're not even done with our rules yet. There are a couple more rules we have to tackle. In general, this maybe is rule 5. I don't know if my rules are going to line up exactly with what the textbook says. In general, you can distribute a power or an exponent across multiplication or division, but you cannot distribute it over addition or subtraction. And so let me show you what I mean by that. So let's look at multiplication first. If I have 3 times 2 and I raise the whole thing to the 4th power, the rules of exponents say that I'm taking the 3 times 2 and I'm multiplying it by itself 4 times. And since it's all multiplication all the way across, I can just rearrange that to 4 3s times 4 2s, which is 3 to the 4th times 2 to the 4th. And I have distributed the power onto the 3 and onto the 2. I could do something more complicated. I could have 2 times x times y, and I could raise that whole thing to the 3rd power. Well, the 2 times the x times the y, there's all multiplication. So I can do the 2 times 3, and then, not 2 times 3, sorry, the 2 raised to the third power, and then x raised to the third power, and then y raised to the third power. And we usually simplify the number. 2 cubed is 8. It works the same way with division. If I have, let's see, let's use 2 and z, and I raise it to the third power. Remember, that's like 2 over z times 2 over z times 2 over z, which I can collect into 2 times 2 times 2 over z times z times z. And guess what? That's 2 cubed over z cubed. I have distributed the cubed to each the top and the bottom. It does not work that way with addition. So let me write warning. If I try 2 plus 3 and I raise it to the second power, well, it's a lot easier just to do the 2 plus 3 first. That's 5 squared, which is 25. This is correct. But if I try to distribute, I would have 2 squared plus, oh, see, I picked the one that does work. There's always an exception, and I picked the exception where it actually does work. Did I? No, I was safe. That's a little tired. I'm a little tired, but I'm doing okay. Let me restart this. Pick one that I've done before and I know will run into an error. If I do 1 plus 3 squared, 1 plus 3 is 4, so I could write 4 squared, which is 16. But if I tried to distribute, I'd have 1 squared plus 3 squared. 1 times 1 is 1. 3 times 3 is 9. And obviously those are not the same answers, and distributing the squared is wrong. So you cannot distribute a power when you have addition. And you also cannot distribute it when you have subtraction. You can only distribute a power when you have all multiplication or a combination in multiplication and division. That's okay too. You can mix multiplication and division, but you can't have any addition or subtraction. All right, I believe there's, well, there are a couple more rules. Yeah. Okay. Nested exponents, like 3 squared raised to the fourth power. Well, I know that the fourth power means I'm going to do 3 squared times itself 4 times. But I also know that 3 squared is 3 times 3. And so I'm going to end up with 1, 2, 3, 4, 5, 6, 7, 8 threes multiplied together. And 3 to the 8th is equal to 3 to the 2 times 4. So when you have nested exponents, you multiply the exponents. And again, it comes exactly from the rules of what exponents are. It's just repeated multiplication. So for nested exponents, you multiply the exponents. For example, if I have x to the 5th and then I cube that, that would be x to the 5 times 3, which is x to the 15. And I could mix things. I could have, let's do x squared divided by y cubed times z to the 4th. And let's raise all of that to the 7. Now I'm going to combine my distribute powers along with my nested powers. I get x to the 2 times 7, which is 14 on the top, and then y to the 3 times 7 is 21, and y to the z to the 4 times 7 as z to the 28th. We're getting close, a couple more. I think there's probably two more. This first one is a two-part rule though. This is rule 7. This one, it comes from the division piece. What if I have 3 squared and I divide it by 3? Well, that's 3 times 3 over 3, and that cancels and it just gives me 3. But also, I could use my rules. I have a two 3s on top and 1 3 on the bottom. So that should be 3 to the 1. 3 to the 1 equals 3. Any number raised to the 1 power is unchanged. I can take 4 to the 1, still 4. I could take -2 to the 1, still -2. I could take 1 over 7 to the 1, still 1 over 7. X to the 1, still x. We usually don't write x to the 1. We usually just write the x. One challenge that I've seen a lot is when students have to do x to the 4 divided by x to the 3. It becomes a lot less challenging if you write it out. So when in doubt, write out the multiplication, and we see a lot of canceling, and we're left with a single x, which makes sense because x to the 4 minus 3 is x to the 1, which equals x. That's the first half of our rule. The second half is a little different, but it also comes from the same idea. What if I do 7 squared and divided it by 7 squared? Well, that's 7 times 7 over 7 times 7. And when I'm all done canceling, well, let's write it as 49 over 49. Any number divided by itself is 1. 7 squared over 7 squared is 1. But my other rules said I should be able to take the 2 on top and the 2 on bottom, subtract them, and that's 7 to the 0. So 7 to the 0 equals 1. Any number raised to the 0 power equals 1. 4 to the 0 equals 1. -3 to the 0 equals 1. 1 over 8 to the 0 equals 1. Any number raised to the 0 power equals 1. And we're almost done. We've got one more rule. And that rule is fractional powers. So far, we have covered integer powers. We know 3 squared is 9, or 7 to the minus 3 is 1 over 7 cubed, which is 1 over 343. And we know that 8, or any number to the 0, is 1. Right? Whole numbers bigger than 0, negative numbers, negative whole numbers, the integers, and 0. Those are our powers. What about fractional powers? Or decimal powers, if you want. And we have notation for that. The square root, which we write as a square root of x, can be written as a power. It's x to the 1/2 power. Once again, this comes directly from one of our other rules. It comes from the nested powers rule. but it's okay if you just remember a square root is x to the 1/2. If I want a cube root, that's to the 1/3 power. If I want a 7th root, that's x to the 1/7 power. So any root, or how about a root of any number can be written as the power made by that number as a fraction. If I want the 4th root of y, I can make this root y to the 1/4 power. And the reason we do that and the reason it works is so that all of our other rules of exponents work. And this allows us to do one other thing, which is now I can do things like x to the 2/3. Well, x to the 2/3 is x squared, but the 3rd power is the 3rd root. So when you have a fractional power, the number on top becomes a power on x, and the number on bottom becomes the root. Y to the 13/7 becomes y to the 13, and then all of that to the 7th root. So any fraction, any fractional power can be written as a combination of a power and a root. There it is. Those are all our rules. All of those rules start and end with the fact that exponentials are just repeated multiplication. And all of these rules just allow us to write that repeated multiplication in a more compact form. And then to combine different terms in different ways. So let's see. I'm going to make another video where I demonstrate these rules and some of the homework questions, because understanding the rules, I think, is best done with very simple examples. But then we need to be able to use these rules on more complicated examples. But I've been talking about these rules for a lot, and you've been watching for a lot, and I think we both deserve a break. So tune back in for the section 4.3 part 2 video. Thanks for watching.